Okay, so let me maybe just go through once. So remember we studied that, these you have already studied, right? We have Pearson's linear correlation coefficient and then we have rank correlation. And we saw the pros and cons and the property invariance that this rank correlation offers us in advantage to the Pearson's linear correlation coefficient. And then we sort of had a look at this example, which kind of conveyed to us that not every time we care about the actual correlation of all the data. Sometimes all we care about might just be a particular tail. So if we are looking at this case, we might be worried more about the lower tail. And that is what sometimes we try to, figure out correlation in. So let us say we're looking at tail dependence. And again, instead of looking at the whole data set and trying to figure out its correlation, if we only care about this box, we know that if we only take this much into account, then the correlation over here would be a better gauge of the tail dependent structure, right? Be it here or in that corner. So we had a look at what happens if these are independent. And then we sort of studied a tool called probability integral transform, which would allow us to take any random variable which might lie between -infinity to infinity and transform it to some numbers between 0 and 1 by keeping its dependence structure intact. So we do not change the properties, we only change the magnitude of the numbers. And that is known as probability integral transform. And what you do is you just define a variable to the cumulative distribution function of the actual variable that you started off with. And once you do that, it turns out that it follows uniform distribution on 0, 1. So life is easy. And we also had a look at its graphical representation of the scaling that happens. So we see the number of the x's which are more likely to occur span on to a steeper u, and thus they span on to project a higher area for this uniform guy. And let's say these values are they do not appear most frequently, they appear only in small fractions. So if you transform them with u, yes, you see that the area here is only this much, which will in essence be equivalent to the area which is here in the triangle. So that was the intuition behind the probability integral transformation. And then we had a look at the coefficients, which will help us determine the kind of dependency that there is in the upper tail as well as in the lower tail. So we look at a formula for the upper tail, which involves looking at the chance that x random variable and y random variable will be observed in somewhere here. And for the lower tail, we looked at something here. So because we looked at here, we saw that x should be less than f small x and y should be less than small y. And small x, as we represented here, is just f inverse u. And here again, because I'm keeping them the same and I'm going to take a square into account, and then this value here and this value here is going to be maybe equal. So I'm going to write a y, small y, which is equal to small x, which is again equal to f inverse u. But again, remember here when I'm saying that I've taken a square, I mind you guys that I haven't taken x and y here, it is x and u here. So actually what we were looking at was something like this. So we have x here and we have a y up here, right, on the y-axis. And the square that I was probably talking about was something like this, where I know that my x and y take equal value. Okay, so any doubts so far? Anyone? Okay, so today what we are going to study is, we're going to see how Copula helps us to merge or couple some things together, and we'll see what it allows us to couple. Okay, so remember when we ended the last lecture, what I was talking about was something I had like that these are my marginals. So this is my marginal for x. If I can maybe write there, this is my marginal for x, and this is going to be my marginal for y. So again, remember for x, I'm increasing in right direction, and here I'm increasing in the north direction. Okay, so I guess that's pretty clear to everyone. But now what I'm going to do is I want to plot the CDFs as well. So remember, we looked at the probability integral transform, right? And now we are going to use that very concept to transform the CDFs that we get for this X and Y into some 0, 1 numbers, which will give us the cumulative distribution function for the joint distribution of X and Y, which is our end goal. Okay, so let me just draw a graph here. Let's say I have this here and I have, okay, maybe I will show you. Just give me a minute. Yeah. Okay. So now if I were to draw the CDF of, let's say, this x-axis, so I have this x variable here, which takes some values. Here I have the marginal drawn. And if I were to draw its CDF, let us say it looks something like this. Okay. And again, we know that the CDF, which is just f of x, cannot take values higher than 1. So its limit is always going to be 1. Okay, and that's it, I guess. So, and we start off at 0. And now let me draw the CDF for this y guy. So what I'm going to do is, I'm going to draw something here. So I have this axis here, and here I'm going to plot the CDF of my y. So remember, why do I plot CDF on the horizontal axis? Because I want to keep these axes, which measures the values that my y variable take, intact for the marginal as well as for the CDF as well. So these are the values that my y is going to take. So it is 0 and then so on here and there. So the CDF, if you have a look, will look something maybe like this. Okay, and again it's gonna be capped at 1. So this is going to be 1. And I'm going to write it like that so that you have an idea that we have, yeah, the numbers on the vertical axis. So now what we have is, this is the CDF of x, this is the CDF of y, and this is the joint of x and y. Okay, so this is the joint PDF for x and y, let's say. And what we want to plot is the joint CDF of x and y, because that is what we care about. So maybe what I can do is, let us say if I'm looking at this particular x, okay, I can have a look at the, for the same x, the marginal value of it. And for the same x, if I extend it up here, what do I get? So let me take another color. And if I extend this guy, let's up here. So remember, I'm going to keep the same x here. And what do I get on the y-axis here? This is the value, f of x. So if I, let's say, put a prime here, x prime and y prime, then I can have something like this. So here, this thing represents f of x prime, right? And now what I have to look at is y. So I extend the same thing for y as well. And I get its CDF right here. So let us say I see that this point is my f inverse. So it's not going to be inverse yet. So it is just going to be your f of y. And because I have written a prime, we have a prime over there just to differentiate. But again, you can write x and y as well. I'm writing prime just so that you don't get confused between this f of x and the f of x that I might write over there. Okay, so all right, what have we yet done? We started off with the joint PDF of x and y, and we saw that for each particular x, we can again go on if we know the value, if we know the function of f of x, that is, if we know this graph, we can again for the same particular x value figure out its individual CDF, and we can do the same thing with the y guy as well. We can figure out its individual CDF right here. Okay, so maybe what I can do at this point is, let me erase this marginals that I have drawn. And now that you guys know that these are indeed the CDFs, what I'm going to do is I'm just going to draw marginals up here. Okay, but again, remember, marginals won't be limited to 0 and 1. So they can take values between anywhere. So they can, in a way, exceed these dotted lines that I have drawn. So let me just maybe rename this. Greater C divided. But yeah. Okay. So let us say this is how the marginals look like. Okay. I mean, I have just plotted them here for the sake of convenience and that we don't lose the marginals. But again, now if we see this graph, we know it represents the marginal X, the marginal PDF, as well as the marginal CDF of X itself, right? And now if we look at this graph, we know what is this? This is just my marginal Y. And remember, if we want to figure out the CDF of joint XY, which is this, what would you do? So basically what I want to figure out is something like this. F of X comma Y. So if I were to plot it here, what would I see? I would basically say that my X should be, less than X and my Y should be less than this Y bar. So I would get this area, right? This whole area is certainly going to be the CDF fxy that I was talking about, right? Do you guys understand the CDF that I have just drawn here? Basically, this yellow is nothing but this. Forget about the limit. I've just written probability that X will be less than X, comma. Instead of this bar, it's a comma, Y less than small y, okay? That's it. And now, using this probability integral transform, what we saw was that I can define another random variable U for my, so this is the value that f of x takes, but you can define a capital U, which is a random variable that your f of x follows, right? So what I'm going to do now is, I'm going to plot that particular random variable here. So again, this is my f of x, remember, and the similar manner. So in the same way I did it for y, I had a y-axis here and I drew its CDF over here, right? Like this. I had x-axis here and I drew its CDF like that. So similar manner, I'm going to take this axis here and we know what is the CDF of f of x. It's going to be capital U. So I'm going to draw something for x-axis as well as for y-axis right here. And I might just define them. Okay, so again, when I want to label this axis now, would anyone want to guess what should be here and what should be up there? Anyone? What do you think will come here? So again, remember, y corresponded to y. X corresponded to the CDF of x. But now what I am going to draw here is this CDF's distribution, right? And again, we know that these CDFs will only take values between 0 and 1. So this 0 will correspond to the 0 here, and this 1 right here will correspond to the 1 here. So this is equal interval, no change in the intervals as well. And again here I'm going to get to the same one. But now if I'm projecting this on this axis, I know that my f of y is what? Something that should come here, right? So I'll instead have my f of y over there. Do you guys agree with this? And here, I'm just going to have my f of x. So I can again define some particular random variables. Let us say now for convenience, I say that this is u and I say that this is v. So what I can do is, if I just mark these boundaries, so it should be somewhere here. Okay, and what will you get here is small u comma small v. So this u will be something which is here on this axis and v will be something that is there on this axis. So maybe I should not write u v just yet. Okay. So what I'm going to do now is we'll trace the locations. Okay. Let us try to trace the locations. So we started off with this x and y, and what we did was we used the same x to figure out its PDF here. So there is a connection that I can draw here. Good. And then what I can do is so arrow can be up there. And then using this f of x, I can again project it onto this axis and figure out a number between 0 and 1, which would follow the same properties as this axis would have. Okay, and I will do the same thing for my y as well. So I'm going to take this axis and oops, it's not going to end there. I'm going to take this and it will go up until here to give me the value of my CDF. And then once I have that, I can again, extend this and this to give me a particular certain coordinate, which will be my u comma v, corresponding to the x bar and y bar that I have. So again, remember this x bar would be corresponding to v and this y bar would be corresponding to this u guy here because of the way I have drawn these diagrams. And again, so this fourth diagram that we have just drawn here is what is copula of x and y. So sometimes what happens is, without even figuring out this blue guys, you can switch on and off between the PDF and the CDF of these joint distributions using just the marginal CDF. And that is the power, because what happens is sometimes you can't necessarily talk about the correlation or the association between the variables by just looking at the joint x and y. So this, once you have this copula function, what you will do is you can trace this back. So in the pink line, I have drawn it in the reverse direction. Let us say you know this copula already. You can use this u, and if you know this f of x, you can trace it back to here and then back to here. And the similar thing you're going to do here as well. So you get back your original coordinates that you care about. So this theorem, so this happens not always, but again, so what did we study in probability integral transform? We studied that this x and this y can also be written as f inverse of u and f inverse of v, right? But if we look at this, it's just gonna be f inverse of v, comma f inverse of u. So I'm playing around with the notations just so that I can give you this nice structure of the connection. But again, it really doesn't matter if you write this as v and if you write this as u, just keep it intact with the notations that I have used before. But again, that's just about it. So again, remember, if I have u and v here, and if I use this f guy here, so what is this f of x bar? It is just u, right? And if I apply f inverse, I apply f on this x, I get u. And if I apply f inverse on this u, I get this value of x bar, which is nothing but this value of x bar here, which is why I have f inverse of v, comma f inverse. So yeah, sorry, I've written this as u, which will just be v. Okay, does this make sense to you guys? So again, I would say, this is just a whole cycle that goes on. But to give you guys something in short, what I can say is that let us say we have this, okay, we have X here and we have Y here, capped at 1, okay, because we're looking at maybe this area. So yeah, and let us say we have this coordinate X comma Y. And what we want is the joint in between 0 and 1. So this is 0 and 1. So from this X and Y, okay, maybe not 1, 1. So from this X and Y, I want it to give me one number which includes the dependency between X and Y together. So that is why this would be my joint that I'm looking at. And this is the marginal X and the marginal Y that I'm looking at. So the thing that is going to help me to get from here to there is copula. So copula will be the function that will allow you to go from marginals to joint. And again, it's just another way of writing copula in terms of math. Now I can maybe write it and you guys will have some idea of why I can write it in such a manner is something like this. So again, I do write X and Y here because my variables will still be Fx and Fy, right? So remember, whenever you think of copula, think of this particular graph here, which takes input f of x and f of y, okay? So you have f of x and you have f of y. And what does it measure? It just measures this fxy joint, which is nothing but the probability that you observe a x less than or equal to x and a y less than or equal to y. So again, you can also rewrite this f of x as u and this as v. So now forget about those v and u switching that I did maybe before. And what you can say is that this copula xy of u comma v is just this fxy. And again, this is for two random variables. And now if you're looking at the multidimensional random variables, you can have u1 comma u2 and so on till let's say ud, and that would just be f x1 x2 so on till xt, and here taking the values x1 x2 and so on till xd. All right, does this make sense? And again, for just like this case where your f of x was u, you will have all of these u1s, u2s, ud equivalent to this f of x, x1. So such that all of your ui's will just be, fi. So it will be fx subscript I. So your u1 will just be fx1 x. So this is just the way you define copula in mathematical terms. So right here. Okay, maybe not here. So this is how copula looks like. And so copula is, just a function that couples two things together. So again, what we looked at here is something that is known as Sklar's theorem. So what it shows us is that we can use these marginals, CDF to map from xy to a point uv, okay? And remember, this uv is something which is there on a unit square, so it doesn't exceed the value of 1 on either of these axes. Okay, so I hope that is clear. And if you have a look at, now, if you have a look at this Sklar's theorem, what it says is that for any f, let me just mention here first that this is Sklar's theorem. Okay, and if I were to write the actual equation that this theorem has, it just says that, let us say if we have a joint cumulative distribution function, which is just the CDF with marginal cumulative distribution functions. So when you read this sentence, you're talking about this thing here, which says that if we have a copula, then we know that we can define F, sorry, we can define, oh, can you guys hear me? Is my connection going? Hello, am I audible?
Yes, ma'am.
Oh, okay, yeah, all right. I guess I thought I wasn't. Okay, but yeah, this is just the summary of this Clark's theorem, I would say, that whenever you are looking at this marginals, you can get to the copula easily using just, a joint CDF and a marginal CDF. And again, if you know that, you have a copula function which already exists, then that will allow you to get to the marginals easily. I mean, you can just couple these marginals together along with the copula and you will get the joint that you care about. So that is the summary of this theorem, I would say. But again, what we can do is, let us have a look at its math as well. So this was just the graph, I would say. But again, so remember, when I'm defining a copula, what does it take as x and y? My capital F of x and my capital F of y, right? So we know that the domain that this copula has will always be between 0 and 1. And again, if I'm looking at two variables, I would write a square bracket 0, 1 and a little 2 above it in the subscript to denote that I'm in 2 dimension. But again, this is not the only property that copula should have. There are 3 actual properties that every copula should follow. So let's have a look at that. Okay, so the very first property states that if I increase, okay, maybe even before I state that property, let me just draw a little graph. Okay, so let us say this is my CDF. Okay, I plot my CDF f of x here, and I have my x variable up here. So if I'm plotting, let's say my x1 here, and if I plot, let's say my x2 there, what do I know about a CDF? What is one of the properties of the CDF? Anyone? That it is always increasing in nature, right? So if I take x2, which has a higher value than x1, then my f of x1 is also going to not be any higher than f of x2. So my f of x2 has to be greater than or equal to f of x1, right? And if I'm assuming that my f of x is a strict increasing function, then there won't even be this equality, right? But again, this is the general case. So the similar thing happens with copula as well. Remember, I can rewrite my copula as a CDF of this joint x and y, right? So copula is nothing but just something like a CDF, okay? And now if I write in, let's say, d-dimensionals, what I'm going to do is I'm going to keep this, I'm just going to change one of these UIs now, and to be consistent with your book, you have UI star, so you will get UD here. So this value will be greater than C of U1, UI, UD. If, can someone tell me what should be the inequality here? Should I write a greater than, should I write a smaller than, or can I write equal to there? Anyone? Greater than, right? So because I'm looking at this copula function being greater than this. So again, what is a copula function? It is just something like a CDF. So again, it is just measuring the area under the curve, right? So here if I have x1, I have this much of area under the curve. And if I even increase a little bit, I know that the area under the curve is definitely going to increase, even though, I mean, how much ever small that is, it will take a value which is higher than the other guy if this is the case. And the next property is again what we have already seen, that the copula should always be between 0 and 1. So it cannot take values beyond 0 and beyond 1. Okay. And the third property is something which I guess is very intuitive as well. So let us say if I give you a copula where all of my other values are 1 except ui. So rest of the values are all 1. What do you guys think it will be? Would anyone want to have a guess at this? So I would say, try to recall the fact, what distribution does my CDF follow? We did derive it using probability integral transform, right? What was the distribution for f of x? Anyone? Okay, we should go back. Yeah, we saw here, right? That the probability that my f of x will be less than or equal to u is nothing but u itself. And why? Because this u is a number between 0 and 1. And that is the only reason you get a u here. And because this is the case, we concluded that my f of x is not only something which is between 0 and 1, but it is indeed a uniform 0, 1, right? So if I say that all of the other guys are 1, and I'm only looking at one particular value, which is this u here. So again, if I think about the area under the curve, it is going to be nothing but just the ui guy right here. Does this make sense? And this will be for all I 1 to d. And again, remember, this also makes sense. Why? Because this, we know that this should always be between 0 and 1, and this ui also always belongs to 0 and 1. It will never exceed. So we know that the area under the curve can also never exceed 0 and 1. So I guess these are the three properties of copula that is essential. Any doubts so far? So again, just to maybe give you guys a bit of a mathematical, I guess we discussed this yesterday, but let me just maybe write it down somewhere here. So here I start off with something where I have values from minus infinity to infinity, right? And because I'm looking at two dimensional, I can just write a square up there. And what I do is I use a copula, which gives me something which is just between 0 and 1. So this is something which is between 0 and 1, and my copula is something which is again between 0 and 1, but a two-dimensional thing. So I get something at the end here, and I start off with this and ending up there. So remember, this is the joint, and copula still has two axes, right? Copula still has an x and a y there, or a y and an x over there. But here we would only have one axis here. So I hope that's clear. And now we can move on to, the crux of this chapter, which is all about the tail dependence. So we will study various kinds of copulas, and all of those copulas will help us to derive some tail dependence structure, and depending on the kind of copula you use again. So not all copulas will give you information about all kind of dependence structures. So again, we defined two different kinds of tails, right? One, we had a lower tail dependence, and the other we had an upper tail dependence. So let us try to have a look at this lower tail dependence formula once again and see if maybe we can write it using the copula. So I'm looking at lower tail dependence. Would someone like to remind me of the formula that there was? So I'm looking at this coefficient, which would just be limit. So because I'm looking at the lower tail, I know I want to approach 0 from above. So that is going to be my limit on what? On u bar. So again, I'm looking at the probability that my x is just less than or equal to small x, which is nothing but f inverse of u, right? And this is given that my y is already lower than this guy. Okay, so remember, this is just my small x and this is just my small y. So now I can rewrite this in, again, limit u going to 0 plus just a simple probability. So I'm going to use my Bayesian formula to dissect this into something like this. So I can now put a comma here, and this will be divided by the probability that I observe this y greater than small y, right? So again, what I can do is I can rewrite this one joint probability as what? As my copula of u comma u upon the probability that my y will exceed the value of y. So again, when I'm doing this, we have to remember the fact that when I write this,
Ma'am,
yes,
in the denominator y it will be greater than equal to y.
oh sorry, it should be less than or equal to, yeah, that's my mistake. Thank you very much. Great observation. Yeah, it should be less than or equal to y. Yeah, I got carried away. Yeah. So again, what I was telling you guys is that remember when I replaced this, what I meant was that my x is nothing but f inverse of u. So what this implies is that my f of x is nothing but u, which again implies that the probability that I observe x less than or equal to this small x is just u, right? And the same is going to be true for y as well. So I can again similarly also write that the probability that my y will be less than or equal to y is just u. So in the denominator here, I would just have a u, and these limits would be as it is. So I have limit u 0 plus, and that's it. And what I did here was I used the fact that this is nothing but my copula, and then maybe I used this fact for the denominator here. Does this make sense to you guys? So now this is the formula for the coefficient of lower tail dependence in terms of copula. Right? So because we know that the domain of copula is u and v, right? So over here I have just taken u. So I have copula u comma u upon u. So I guess this is pretty much straightforward. And in a similar manner, we can also have a look at upper tail dependence. So again, whenever I'm looking at upper tail dependence, what is my formula? I'm looking at lambda u, which is its coefficient. And because I'm looking at the upper region, I approach 1 from below. And again, I have u, and I'm looking at the probability that my x will be greater than or equal to f inverse of x, such that my y is already greater than this. Oops, I shouldn't be writing x in there. It should just be u. Right? Okay. So now that we have this already, what should we do? So again, we do the same, we use the same kind of technique that we used previously, and we'll try to write this in terms of probability. So we get 1 minus probability that my x will be greater than or equal to x, such that my y will be greater than or equal to y. And I will just, again, I use my Bayesian formula, and what I will get is probability that my x takes a value higher than x, comma, the probability that my y takes a value higher than y, upon the probability that my y takes a value higher than y. Does it make sense so far? Okay. So now what I have to do is, I have to use something here. How can I rewrite my numerator as? So again, remember, whenever we are looking at greater than symbols, what helps us more is to look at it in terms of the CDF. So whenever we look at something like this in the denominator, let's say, what I'm going to do is I'm just going to rewrite it as probability as 1 minus the probability that I observe y less than or equal to some y, right? And this again is going to be just equal to my u there. But what about the numerator? So again, to think about this case, what will help is to have a look at the Venn diagram. Okay, so Venn diagrams, John Venn was the guy who invented these diagrams, which I would say are pretty convenient, and I really like this diagram just for the simplistic nature of it. So whenever we are talking about something, let's say, so this region right here, maybe I can use some another color. So this region right here, let us say that this is, so let us say that this circle corresponds to the probability that my x is less than x, and this circle corresponds to the probability that my y is less than or equal to y. So this pin graph is something where these both guys are true, right? So this is just going to be something, let's say this. Okay. And now the rest of this stuff outside everywhere is what? It is probability that you observe x greater than or equal to x, comma y greater than or equal to y. So all of these, this and that sums up to 1, right? Because we know that this universe consists of one probability, and then we are defining these circles and these areas within them. So if I have to write this probability that my x will be greater than x comma y will be greater than y, in terms of this guy, what will I have to do? I can't simply write it in terms of that, right? Basically, I want to take into account this orange region. So what I can do is I can take this 1 and I can maybe subtract this much of the area from within the 1. So what I rewrite it as, let me just use blue. So I'll rewrite it as 1 minus. So first of all, sometimes we also have information. I mean, we also know, right, that this is going to just be u. So we can use this. And what I can do is 1 minus probability that I observe x less than x plus the probability that I observe y less than y, right? So what I have done is I've taken this 1 and I've subtracted this circle first, and then I've subtracted this circle. So when I subtracted both of this circle, I subtracted this region twice. So I will have to add in this guy once. So this is what I'm left with at the end. Okay. And now if I try to look at it further using just, what I already know of. So what I get here is 1 minus. So this is nothing but probability that x is less than or equal to x. So what is this? U, right? And what is this? U. And what do we know about this guy? Do we know what the value is for this guy? Anyone? Do we know the value of this guy? So if you have a look at the lower tree dependence, what was it? It was exactly this, right? What did we use? We used the copula, u comma u. So that is the same thing that you're going to use here. You will get here copula u comma u. So remember, whenever I'm looking at the joint CDF, that is my copula, right? Because if you have a look at this graph here of copula, we have joint CDF. So I guess that is it about the upper tail dependence. So if you try to write it nicely, lambda u will just be equal to, limit u going to 1 from below, and you will have 1 minus 2u minus copula u comma u. And this everything will be upon 1 minus u. Oh, did I?
Shouldn't that be like outside the probability of x less than equal to x and y less than equal to y outside the bracket?
Yeah, so yeah, if I put it inside the bracket, it's sign will just change to minus, right? So instead of, so I think I explained it correctly, but I just wrote it incorrectly. Okay.
Yes.
Yeah. So what I meant to say is we add these two circles twice. So we have basically added this region twice, but we only have to subtract this once. So we also need to subtract this region once again. So I guess now it's correct. Thank you very much. But yeah. So this is the formula for the coefficient of your upper tail dependence. So again, these are really general formulas, right? We haven't yet defined this cu comma u, and which is what we are going to do later on in this whole chapter. So we are going to take various occasions. So sometimes we would have that, x and y are independent. So if we have that information a priori, we can use something to figure out the actual expression for this cu comma u. Okay, and I guess we would be using that sometimes as well. But again, I guess that's it. And sometimes what you can do is, I guess maybe I can just write it here. And there's always some space here. Okay, so what I was telling you guys is about something lambda u. So now, as of now, I'm seeing that its limit u goes to 1 minus, right? And I've started with the probability that my x is greater than x, comma y is greater than y, upon the probability that my y is greater than y. So this can actually also be written as u going to 1 minus. So, okay, maybe before we do this, we need to study something else. I'll come back to that part, okay? So, now let us define, okay, do you guys know the concept of complement? Basically, if I'm talking about this blue space, this orange space is the complement to this blue space, okay? So let's say if I'm talking about the probability that A will occur, its complement would be the probability that A does not occur. So that both of them always add up to 1. So whenever I'm talking about this copula, which I just wrote, what I am doing is f of xy, x comma y complement. So we know, so again remember what happens here is, the only confusion that tends to occur here is that this f complement and this f will not sum up to 1, right? Because what is your f? F is the fact that you observe this less than or equal to x and y less than or equal to y, which is this, and the orange guy is this. So the complement, we don't take the marginals into account. We are looking at only the joint. So look at it in terms of copula, where you only have one distribution, which is this f of xy, okay? And then you would say that if we look at it in terms of this xy joint, these complement and the other f of xy would actually sum up to 1, because you would either observe this or that. But again, now that we have this, remember that again, even if you're looking at something like this in a quadrant, let's say you have x here, you have y here, small x here, small y here, something less than is this. So both we observe less than x and we observe less than y. But if you're talking about the greater than, we observe something here, right? So we'll forget about the cases where these happen and these are happening. So again, it need not always sum up to 1 in this kind of complementarity, where we don't look at this x, y simultaneously, but x on one axis and y on the other axis. So that is what we're doing here. So again, what I can do is I can rewrite this thing, which is just f complement, as c complement as well. So what is c complement? It is just the copula that I'm putting a complement on, but again, its domain is going to stay intact. what did I even write? Should be y. I mean, I can still put x, but yeah, I'm gonna go with y here. So again, whenever I'm talking about this f of x, I know what is this. This is just 1 minus the probability that I will observe x greater than or equal to x. So this is also the complement of something that we would have written in this case, right? Which is x greater than or equal to x. So these kind of copulas are known as survival copula. And why survival? So sometimes you have a look at survival function, which will just ask you something like this. So let us say I have lived up until now. What is the chance that I will still be alive for the next year? So probability that my y is greater than y. I mean, there wouldn't be a comma here. Instead, there would be a bar here to denote that this has already happened. So the fact that I have lived up until now, so my y is today, and the fact, and given this, what is the chance that I will live for the next 1 year as well? So that is why this is also sometimes known as survival copula. And what happens here is you represent this with a copula. So again, when I'm talking about this C bar here, I can replace this f of x with 1 minus probability that my x will be greater than or equal to x, right? And again, if I'm looking at this, you will take something of, because we're looking at again complements here, you have 1 minus v there, and what you get is something like, oh, okay, so again, I forgot to say, we have f bar and y bar here. So these aren't only f of x and f of y, these are indeed f bar and y bar. So what will this be? This will be 1 minus f of x, right? So this will be 1 minus the probability that you observe x less than or equal to x. So that you get, so this is nothing but u, right? So you get 1 minus u and 1 minus y up there. And if you solve for this, so basically you, when I say you want to solve for this, I just mean that you substitute this and this value in the function that we derived here somehow. But again, you won't always have to do that. So what you would get here is something like this: 1 minus u minus v plus c of u comma v. And this is what you get, because again, we're looking at this complement. So this is nothing but this, okay? I'm looking at x greater than or equal to x and y greater than or equal to y. So again, remember, this is not the given part. So we are only looking at the numerator part here. I'm only looking at the comma factor, which is why I have written only the numerator and not the 1 minus u part, and not the limits as well, because again, we didn't have limits here. So maybe I should just write here, only the numerator part. So now that I have already defined my survival copula, I will use the same notation to rewrite this numerator here. So what I will get is something like C bar 1 minus u comma 1 minus v upon 1 minus u. So the denominator is going to still be the same, and only the numerator changes. So remember, what we are doing is we are approaching 1 from below, and again we are still looking at this corner itself. We aren't looking at something else, we are still looking at this corner. But again, what I'm doing is I'm approaching 1 from below, and I can just rewrite this in terms of the survival copula. The survival copula is nothing but C bar, which acts as, just to understand what it means, you can think of it as complement as well. So this C bar 1 minus u comma 1 minus v. But again, remember, I think here here I didn't specifically mention. So I was assuming that this is u and this corresponds to v. But here I did use u and u for both of these guys, right? So what I should ideally write instead of v here is just something like u. And again, this could actually be rewritten by changing its limits from u approaching to 1 from below to approaching 0 from above, and again you have this C bar. So now instead of 1 minus u and 1 minus u, what you are going to have is u comma u, and this will be upon u. So again, why you can do this? Because we know for sure that u takes only values between 0 and 1, right? So 1 minus u, if u is approaching 1, then 1 minus u is going to be 0. And if I write u here, u is approaching 0. So it kind of complements. But again, you don't necessarily have to, get into the nitty-gritties of this, because what is going to matter, at least from the exam point of view, is the types of copula that we will be studying now. So any doubts so far? Anyone? So what is the most important thing here is to understand what a copula is, what it couples together, what it gives us at the end, and some of the properties that it always has to follow, then the lower tail dependence, then the upper tail dependence formula, and this survival copula. This might look a bit complicated now, but I think if you sit with it once, it will come to you easily. The dots will connect. But any doubts so far, anyone? No doubts? Okay, so maybe what we can do now, what's the time? I guess we still have 1 hour left, right? Oh, that's good. So we can actually study the types of copula as well. Okay, so again, we will, study 3 different types of copula, main copulas. So one would be fundamental copula, second would be explicit copula, and third would be implicit copula. So again, when I talk about fundamental copulas, these are really, fundamental in nature. So the relationships that we observe are very fundamental. So the first relationship would just be, that these X and Y, they are independent. The second would be that these are perfectly correlated, so 1. And the third would be that these are negatively correlated, so -1, and sort of something like that. And again, then you will study about explicit copulas. And again, the reason we call them explicit copulas is because we can explicitly write their functional form of the copula again. And whenever we're talking about implicit copulas, we cannot necessarily, write a closed form solution for those implicit copulas, but we'll use a particular function, and I'll show you guys how to even, build a copula up by yourself. And then we'll use that particular, it's called a generator function. We will generate a copula using that particular function. And sometimes when we can't really figure out a closed form solution for this copula, we keep it in terms of that generator function. But again, before we move on to that complexity, I think let's just start with, fundamental copulas. So let me maybe just, oh, there are only 3 students today. Wow. Okay, so let me just write fundamental copulas. So there are 3 basic types of copulas, and the very first, which is the easiest one, I would say all of these 3 are really, nothing much. So we have independence copula here. So whenever I say that X and Y are independent, what is the first thing that comes to your mind? Tell me. Anyone? So let's say if I tell you that this X random variable and this Y random variable are independent, then what should happen? Can you guys hear me? what are the properties that variables PDF, so I'm giving you a hint that it does involve the PDF, should satisfy for these two variables to be independent of each other?
Joint PDF should be equal to multiplication of individual PDFs.
Exactly, right? Your joint PDF should be ideally equal to the multiplication of individual PDFs. Exactly. And that is the same kind of thing that, oops, yeah. So that is the same kind of thing that happens with Copula as well. So remember, Copula is not the marginal. So Copula is not the, PDF. It is something like a CDF, right? But again, just to remember it easily, it is going to just be U times U. So remember what we did here was we actually derived this upper tail dependence and the lower tail dependence coefficient in terms of C of U comma U, right? And we are still wondering what is the value of that C U comma U or U comma V. So again, if we know that we're looking at the fundamental Copula, and again, if we know that X and Y are independent in nature, then we know that the Copula value will just U times V. So again, what is my U? My U is just F of X. And what is my V? It is just F of Y. So remember, what is capital U and capital V? It is the CDF of this F of X and this F of Y, right? So again, just to be precise, we have this. So now if we try to derive those tail dependence formula, so let us say we look at the lower tail dependence first. What was the formula? It was something like this, right? So because lower tail, we are approaching 0 from above. And again, we had U. So we had something like this, U comma U upon U. So now what will happen in this case is, I'll just have limit U going to 0 plus C of U comma U is going to just be U square upon U, which will get cancelled, and what I'll be left with is 0 at the end, because if my U goes to 0 and I only have U in limit, so it's always going to be 0 in limit as well, right? So I guess that was it about the lower tail dependence. But now if you have a look at upper tail dependence, let's see what happens. So my lambda U was something like 1 minus U minus U, and then I guess I had a plus U square, right? So because my Copula is now going to be U square, okay, minus 2U. I can also write this. Yeah, it's fine. And I have 1 minus U, but I forgot to write the limits. So the limit when I'm approaching U 1 from below. Okay, so we now have this. So again, I have limit U going to 1 minus 2U plus U square upon 1 minus U, which I can again rewrite as 1 minus U square upon 1 minus U, which will just cancel each other out. And what I have at the end is 0 here. So again, this is what we would have expected, right? So because we're looking at independence Copula, if I'm looking at X here and Y here, I know there shouldn't be any tail dependency, be it either the lower tail or the upper tail. And that is indeed what you get. So lower tail dependency is 0 and upper tail dependency is 0 again. So it kind of just confirms the fact that you were looking at independence Copula. So sometimes you necessarily do not know if whether from the start what kind of Copula that it is. But again, you can just have a look at the graphs. And I think in R, you would have this special packages, okay, wherein you won't even have to substitute this. You won't even have to define the Copula function and everything. You just type Gumbel, you just type Clayton, you will get the answers right there and there. But again, that was it about the independence Copula. So the second type of Copula that you can have is the one where X and Y go together. So when I say they go together, I mean co-monotonic Copula. This is another kind of fundamental Copula. But again, before writing what this Copula function is, so I want to look at what this will be if my X and Y go in tandem. Let's add this. why here x there? So when I'm talking about common alternative, I know that there is a perfect positive correlation among these variables, x and y. Okay. So let us have a look at an example first. Again, this example, I'm just going to take it from your book, but you can also, basically take any other example as well. So what I'm looking at is y equals to x plus 0.01. Okay, so this is what I'm looking at. And again, now you can clearly see from this function itself, if I increase my value of x, my y is also going to increase, right? There is no nothing else playing in around here. Okay, so again, just to have a look at, the copula. So remember, whenever I'm looking at copula, what is it? It is f of x, y. So what I care about is this, right? So now I can just rewrite this y in terms of this x here. So I can write this as this, comma, x plus 0.01 less than or equal to y. But again, what I can do is, instead of writing this as separately, I can just take the 0.01 from the left-hand side to the RHS and write this as x less than or equal to y minus 0.01, right? And that is all you have. But again, now I can maybe draw a number line. So I want my x to be less than x, and I want my x to be less than y minus 0.01 as well. So if I want my x to be less than this, and if I want my x to be less than this, and again, I'm not looking at either this or this, I'm looking at this and this. So I want both of these to appear simultaneously, so I know the region that I care about is this. But again, we don't know for sure whether my x takes a lower value or this guy takes a lower value. So what I can write this as is the probability that my x will be less than or equal to whatever the minimum of this x guy and this guy is, right? So if my x, let's say, comes here, if my x takes a value lower than this guy, then I know that my x should only be less than or equal to x, because that would in a way imply that it is also less than or equal to this guy right here, right? So now what I'm going to do is I'm just going to rewrite this. So I'm going to take this minimum outside and I rewrite this as the probability that my x will be less than or equal to x, comma, the probability that my x will be less than or equal to y minus 0.01. And again, why I can do this? So let us assume that this is the one which takes the minimum value. So what we care about is this area here. So if this takes a minimum value, we know the area over here is going to, of course, be lesser than the whole area here. So I guess this makes intuitive sense. So now if once I have rewrite this as this, what I can use is, I can write this probability that my x will be less than or equal to x as what? As f of x. This is nothing but my f of x, comma. Now I will rewrite this x in terms of this y here. So let us say I only take this now. What will I have? I have probability of y plus 0.01 less, y minus. So I'll have a y minus, right? Because I'm writing x less than or equal to y minus 0.01. And that would again cancel each other out and you will be left with only something like this. And so at the end, what you have is minimum of f of x, comma, f of y. And again, if we recall, we denoted this f of x as what? As u, and we denoted this f of y as v. So what you have here is indeed a minimum of u, comma, v. So that is how you define your common alternate copula. Does this make some sense? So again, I can just write it here that this is u and this is v. Oh, just Any doubts so far? No doubts? Okay, so I guess in a similar manner, we can do the same thing for the case where I have the relationship between x and y, not a perfect positive, but let's say something like this. It's going to be a perfect negative. So as in when I increase my x, my value of y decreases. And this is known as counter monotonic. And I would say the best example for this would just be, y equal to minus x. Because if you increase your x, you have a minus sign here, so your y is of course going to decrease with an increase in x. So now if we try to figure out the copula, let's say for this, okay, so I'm looking at fxy, and again I would write the same thing here. So ideally, I guess you guys should try this out by yourself. And if you want to, just let me know. Do you guys want to try this out by yourself? So you are going to do the same thing, okay, that you did here. Or maybe you guys can guide me and we can do it simultaneously over here. So now I want to replace this y. So I will just write, minus x less than or equal to y. Okay, now what should I do next? Anyone? So we have a random variable x, and here we have a random variable minus x. But we know that we only have information about the random variable y and the random variable x. So what is it that I can do here to get something in terms of the information that I already possess? Yes, so remember the copula function that I have. So I forgot to write here. So the copula function that I care about is P of u comma v, right? So I want something in terms of u and v. And what is my u and what is my v? My u is f of x and my v is f of y, right? So maybe somehow I want to use what I have on the board to derive an equation in terms of fx and fy, such that I can replace them with u and v to get to the value that my copula should have, right? Yeah, so go on. What do you guys think is this? Are you guys there? Can I have a hello from everyone at least?
Ma'am, if we change like minus x, we have minus x is less than equal to y. So if we do it like x is greater than equal to minus y, then we like is.
Yes. And I think that is exactly what we should be doing, right? Because we know things about x and we don't know anything about minus x. So it's better if we can convert it into x. So again, if I have a minus here, I will do minus here and my inequality will change. So what I have is that my x should be greater than or equal to minus y, but it should be less than or equal to y, right? Okay. So there was a big mistake. This shouldn't be y, right? My x should be less than x. Yeah. So that is what you get. So to figure out this probability, let us try to maybe, have a line here. So we have a minus y here, we have a x here, right? What I want is the chance that my variable will lie within this range. So what I can do is I can just subtract the probability that my x will be less than or equal to x, which is this, and then I can subtract this much. So minus the probability that my x will be less than or equal to minus y, right? And again, what I'm going to do is, once I have done this, I will replace this x as minus x, which takes a value greater than y. And again, I will just replace minus x with a y. So I have that my y takes a value greater than or equal to y. But again, I want something in terms of fy. So I replace this as 1 plus probability that I observe y less than or equal to y. So if you were to write it in terms of Copula, what you would have here is, let's say fx, fy, which is just v, and this is just going to be u, right? So what you get here is u plus v minus 1. So does this solve our problem? I guess the very first thing that we should always do is, once we write any formula for Copula, is to check whether it satisfies all the properties of Copula, okay? So if I write this Copula u comma v in the counter monotonic case as u plus v minus 1, is this enough? So let us say my u has a value of 0.8 and my v has a value of 0.8. What will I have? What will be the value of my Copula? Anyone? So if my u is 0.8 and if my v is 0.8, what will be the value of my Copula here?
0.6.
0.6, right? So 0.16 minus 1. Sorry, 0.8 plus 0.8 will be 1.6 and you will subtract 1 from it, so you get 0.6, right? That's it. But let us say if my u has a value 0.2 and my v has a value 0.3, then what will be the value of my Copula? It will go negative, right? But we know that Copula measures, it is just like a CDF, right? So it cannot take values beyond 0. So what you do here is, you just tweak this a bit and you write a 0 here. And you define that this Copula is a maximum over this interval. So let us say anytime you get a negative number for this guy, we know that the maximum between this and 0 is always going to be 0, right? So again, what happens with probability is, you cannot necessarily, not make it negative, but you can just put a 0 here, because you know that once my x takes negative value and my y takes negative value, then the area here is just going to be 0, because all of my distribution lies up there. So the area here is just going to be 0. So it doesn't matter if you write it this way, just so that, it could follow all the properties that we have justified before for it to behave like, a proper Copula. So I guess that's it about counter monotonic Copula. But again, now what the question is, what do you do? So, okay, also one more thing, I guess this is a very important thing. So one property of Copula was that it is increasing in nature. And the second one was that it takes a value between 0 and 1. And the third one as well. So again, remember when we defined the properties, we wrote Copulas as in D dimensions, right? We had D random variables and we wrote C of U1, U2 till UD. But again, whenever we're looking at this kind of a copula, let us say we're looking at combinatorial copula, we can look at X, Y, Z, and so on as well. And once you increase the value of Y, the value of Z will also increase, the value of X will also increase. So that is good. But again, if you're looking at counter monotonic copula, and let us say you have X, Y, Z. So if you increase X, your Y decreases, then whatever you do for Z, be it either increase or decrease, it's gonna become co-monotonic with either X or Y. So you cannot have more than two variables counter monotonic behaving counter monotonically simultaneously. So that is something that is a limitation, but again, it just makes sense. Okay, so maybe now we can have a look at, how do we actually model these copulas and basically how do we simulate these copulas. So again, what's going to happen is generally, again, in terms of, I guess we have only drawn, this is for counter monotonic copula. Then we have also drawn for combinatorial copula, and for independence copula, you would just have something like random, right? You have no correlation between X and Y. So this is X and this is Y. So it's just going to be really random. So again, now what I'm going to look at is the copula itself. So let us say I'm looking at a combinatorial. I think we should first look at counter monotonic copula. So let us say if I'm looking at the counter monotonic copula, and I tell you guys that my value of U. So again, now what I'm going to do is I'm going to plot this copula here. So what I'm going to write here is U and V here. Okay. So remember, if I tell you that my random variable U takes a value small u, then can you tell me what will be the value of my V here? If I'm saying that these are counter monotonic copula. So let us say we simulate a particular random number between 0 and 1, which is U, and I want it to, be counter monotonic. So what will be the value of V? Can I deduce any value of V just by knowing the value of U? So let me give you guys an example, okay? So let us say if I tell you that my value of U is 1, what will be the value of V? So look at the graph, okay? I have drawn a line here and I know the maximum value that my U and V can take is only 1. So if my U takes a value 1, my V takes a value 0. And if my V takes a value 1, my U takes a value 0. So I know whatever value my U will take, my V will always be just 1 minus of that particular number. Right? So V is going to be nothing but 1 minus U. If U takes a value U. So there is no other value that this V can take. It always has to be 1 minus U. So again, when I do this, I'm assuming that this has created a 45-degree angle here, which is what it does. So this is a perfectly negative correlation sort of a scenario. And again, if you have a look here, this is like a perfectly positive scenario. And again, I will just remove this. And I will write U here and I will write a V up there, right? So now if I tell you guys that my U, that this U variable takes a value U, can you tell me what value my V variable should take? So again, let's say this is the value that it takes. What is the corresponding value for V here? Anyone in terms of U? Can you guess this? So again, I'm looking at a perfectly positive relationship. So remember, the confusion that might happen is sometimes if you think of u and v as x and y, which you should not do, okay? Think of u and v as copulas itself. Sorry, not copula, but the domain of copula and f of x and f of y. Do not think of them as, x and y. Think of them as f of x and f of y. Yeah, so if let's say I'm looking at the common alternate copula, what do you guys think the value of my v will be in terms of u if my random variable u takes a value u, small u? Anyone? Are you guys thinking about it? Can you guys hear me? Hello? Are you guys there?
Yes, ma'am.
Yeah. So are you guys thinking about it?
Ma'am, will it be u plus or minus something or a multiple of u?
Or a multiple of u, you said?
Yes, ma'am.
Okay. So let us have a look. So what did I use to, figure out the value of my v in this case? I tried to substitute the value for u, which the easier case is just to substitute 1, right? And I saw what is my value for v? 0. So let us try to do the same thing here. Let us say this is, let's say, the maximum, okay? So this is 1 here and this is 1 here. So if my u takes a value 1, what is the value of my v? So this is like, positively, when I'm saying that I'm looking at a perfectly positive correlation, this is of course a 45-degree line which just mirrors the y-axis onto x-axis, right? So if my u takes a value 1, my v is also going to take a value 1. So if I tell you that my u takes a value small u, my random variable v will also take the same value, which is small u. Does this make sense?
Yes, ma'am.
What about others?
Yes, ma'am.
All right. So I guess this was about, so what happens whenever you try to simulate these random numbers, you can just write, R, U, and IF. So you're going to generate some random uniform numbers, and that would be between 0, 1. So you can write that as well, R, U, and IF 0, 1. And you would generate easily a random number between 0, 1. And again, depending on on the kind of copula you are simulating for, you can denote the value of your V as well. But again, if you're looking at independence copula, then you would have to generate 2 random numbers. And they can be same, they cannot be same, they can be just, one minus the other, but that would just be, the independence nature. I mean, that would still be independent. I mean, if you generate some sort of number. But when we're writing in terms of math, you can just write that u will be a number between 0, 1 and v will be another number which is between 0, 1. And now I guess, so how many of you guys have heard of utility function before? Have you guys heard of utility function before? So it is actually, just, so in economics, whenever you try to study microeconomics at least, you study graphs. Okay, something like this. So you have a graph, then you have this graph, then you have this graph. So these represents the utility that an individual gets by having a good which is on the x-axis and a y-axis. So there is some particular combination of x and y, and then there is another some particular combination of x and y, and all of these combinations of x and y give the consumer a utility of 3, which is why this curve represents all the possible combinations of x and y, which will give this consumer a utility of 3. And the same can be said for this. So again, as in when I increase the value of x and I increase the value of y, I'm assuming that the consumer gains more utility by consuming more of a particular good. So this curve, as in when you go towards the right in the north direction, you get higher and higher utilities. And again, these curves actually have a name, and these are called indifference curve. Indifference, why? Because on this particular curve, it doesn't matter where you are going to be indifferent because the utility at the end is just 3. So no matter how much you consume x and how much you consume y. Yeah, I mean, you can consume more of x and less of y, or you can consume less of x and more of y. You would have a utility of 3 only. So this is only half of the diagram that is shown. So again, if I were to explain this, so this is in terms of, like a 2D plot, right? So now if I were to explain the same concept to you guys in terms of 3D, what I would do is, I would want you guys to imagine that this is a hill, okay? I mean, by hill, I mean H-I-L-L, okay? This is a climbing hill that I am on. And okay, let me say that, I'm defining my axis here. So this is this x-axis and this is some another axis. Forget about what is x and what is y. And again, remember, because I'm looking at the 3D, I also have some another axis here. So you can just have a look at the room that you're sitting right now in and just concentrate on one particular corner. You see 3 lines, right? One that goes up, one that goes in the length, and the other that goes in the breadth of your room. So you can say that the length and breadth are x and y axis, and the height, which goes up, is the z axis. So this is your z, let's say this is your x, and this is your y. Okay. So now what I'm going to do is, I'm going to create layers. So let us say I divide your row. So I think it's easy with the example of hill as well. So let us say you are climbing a hill. So you will have something, let's say like this. we will have to climb the hills, right? So ghat type, I mean, if you have traveled, I don't know, but this is something like that, okay? So yeah, what you do is, if you want to climb this hill, you're, let's say now here, you start, okay, let's say you are here, the way I have drawn, let's say you're here, and if you start from here, you walk, 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 and then you again walk in the similar fashion to reach to the top of this hill right here. Okay. So what happens is, when you're walking on this path, your coordinate of y and your coordinate of x is varying, right? So depending on wherever you are, but your xz coordinate stays as it is. So whenever I'm talking about z, you can just say that, this is the measure of height from the ground. So if you take the example of your room, what you can do is you can just divide your room into layers like this. And what you're doing is you're walking from one side of the room to the other side of the room on one particular layer, so that your height from the ground stays the same, but again your length and breadth coordinates are changing. So that is what is happening here. And again, what happens is, whenever, let's say if you are somewhere here, so let us say the height from the ground is 3. And if you're here, the height from the ground is 4. If you're here, the height from the ground is 5. So this is just a 3D representation of the same thing that I have drawn here. So maybe I can also, so in terms of heel, what you will have is also on the front side, also on the back side, right? So you can maybe draw a little circle here, which represents a height of 3 from the ground. Then you can represent another circle, which is again going to be, so again, you see I'm drawing concentric circles, and this gives you an idea that, a hill would be wider here, then it's going to, not be that wide as well. So I have a smaller circle here. This is for 3, this is for 4, and then this is for 5. So, this would be, so you can give that effect again, so it is, so this is popping out, okay? So imagine a hill coming from my board right in the air now. But what I've done is I've cushioned it. So what I'm doing is I'm placing my hand on this hill from the top, and I'm just, basically uska chapta kar de rahi hu main. So I flatten it out on the ground, and this is what I get. This is 5, this is 4, and then this is 3. So this is what I have. But what I have here, so in terms of economics, they don't show you the rest of this. This part is ignored, and we only care about these, which is what you see here. But this is, these are actually known as contour plots. So maybe if you study mathematics, you might be studying, something about convex and concavity of these things. And again, the very fact that you only care about these is because that, you assume the individuals are risk averse in nature, and only if someone is studying economics, you should care about, knowing that. But again, I think it was just a good introduction before I show you guys how these copulas actually look like. So let me pull up something. Any doubts so far? Go. Can you guys see my screen? Can you guys see an image on the screen?
Yes, ma'am.
Yes, yes. Okay, yeah. All right. So, okay, here what I have is just, something. So, if you have a look at this, so what I have done here is you don't necessarily know what is on the x-axis and what's on the y-axis, okay? But if I were to just show you guys this diagram, and if I were to ask you guys, what do you guys say the correlation is between what is there on the x-axis and what is there on the y-axis? What would you guys answer? How does this look like?
No correlation, right?
No correlation, right? I mean, it looks as if, these are just random dots around in this square. But indeed, actually, what it was is the rank of the CEO payment and the rank of the stock return. So there was a study done by some people. What they were trying to say is whether if a CEO is paid higher or not has any effect on the stock return from that one particular company. And they saw that there is actually indeed, nothing going on over there in terms of at least association. And okay, so this is how an independence. Can you guys see this, or should I read this? Yeah, maybe now it's much better, right? So this is how an independent copula would look like. But again, there are, so again, you can have two different distributions and still have the same copula. So copulas are not always unique in nature, I would say. But again, not every copula that is independent will look same as well. But yeah, independence copula can still exist in general. And there are some bounds that we'll study soon. But yeah, okay. So this we are going to study soon. So whenever I was talking about, that some copulas are very well in capturing only the lower tail. So Clayton copula is one of those copulas. So if you, maybe I can just explain it now. But so Clayton copula is actually, one of the explicit copulas for which you do have a formula. But again, if I tell you that, my x takes a value this big, then what is the value that my y will take? So you can choose amongst any of these values, right? So you can't for sure say what value your y will take. But if you say that my x takes a value here, you only have to look at this box, right? So you can for sure say that if your x is lower, then your y will also be lower. So you see that Clayton copula captures the lower tail dependency much better than any other kind of dependency. And if you have a look at dumbbell copula, you can't necessarily say something here. But if you are in this upper tail, you can actually say that, if your x takes a value which is higher, your y will also take a value which is going to be higher. So yeah, this will be better in capturing the upper tail dependence. And these copulas, so I guess this is a T copula and this is a Gaussian copula. So again, if you have a look at this Gaussian copula, you see that if x takes a higher value, you can't necessarily say that, what value your y is going to take. And again, here you can't necessarily say what value your y is going to take. And I think this Gaussian copula was actually the one which led to the financial crisis. So Gaussian copula was the copula that these finance guys were using to price the securities. And I guess, I forgot to put the video. I have this put in the article, and I guess it is from the Wired magazine, not from the Wall Street Journal that I thought it was. But yeah, I guess you should give it a read to, just see the importance of knowing the assumptions that the tools that you use operate upon. And I guess it's just nice to be aware of the limitations of the tools and techniques that you are studying. And it's equally important as knowing how it works as much as it is to knowing when it does not. So yeah, that's it. But again, if you have a look at T copula, the tails are a bit fatter. So here you don't see much variation, but here you do see a lot of variation. So it basically says that if you have a higher value of X, you still can experience this lower value of Y. But here it's really, not blank. I mean, it's really blank. So you see that here this guy has a fatter tails, and of course, as we know, if normal distribution is something like this, your T will of course have fatter tails than what a normal distribution would have. So I guess that was it. But again, I will show you guys how this looked like, and now I don't know how to scroll down. Okay, yeah. Okay, yeah. So this is actually a Copula density. Again, this is just my U and this is just my V, and this is my Copula. So when I'm saying density, I'm in a PDF because I know that this is 3. So if value of Copula is something like 3, I mean, it's certainly not a CDF for sure. So this is the PDF. So small f x y. And this is the value of U and this is the value of V. So for each value of U and for each value of V, so this is like, your room. So you imagine this is a net and art installation in your room. And yeah, I mean, I think I find this Copulas very intriguing because it's pretty as well, I would say. So yeah, and this is actually a Gaussian Copula. I mean, this is what it looks like. Just like a clothes, maybe, Aladdin's mat floating around here, I would say. That is what it reminds me of. But yeah, I guess this is what I wanted to explain to you guys now. So here I have 3 different graphs, which represents the 3 different types of fundamental copulas that we just had a look at. So remember, there was one case where these guys were independent. So my copula, if let's say I'm looking at U comma V, was just U times V, right? So if I'm looking at independence copula, I get something like this. So again, remember, this height represents my copula, U comma V, and this, let's say, represents my V, and this, let's say, represents my U. Okay, so what I know about this copula is, for each value of U and for each value of V, it takes a particular height, and that height is measured on this copula axism. Maybe it's not quite evident in this case, I would say. So I guess we can have a look at this case first. So can you see this? So this is again your U, this is again your V, and this is again your copula U comma V. But again, to figure out what kind of a case this is, let us see what's happening over there. So can you guys guess what's happening over there? So let us say if I say that the value of U here is 1. Okay, and my value of V is also 1. Then what is the value of my copula? Can you see it here? So, okay, maybe forget that. Let us start with something like this. So let us say my value of U here is, I guess this is 0.2. So let us say my value of U is 0.2 and my value of V is also 0.2. So what is my value of copula? It is 0, right? Because this triangle, so this whole triangle is of height 0 from the ground, and this is what you have. So imagine your room. Imagine that this is your room, and this is the first wall, and this is the second wall of your room. Okay, and maybe I'm distorting this picture for you guys by drawing lines upon it. But can you guys visualize something that covers the diagonal and the half of your room on the floor, and then you just take rest of the cloth and join it to the tip of your room? So this is how this copula would look like. So it is just a flat, plain kind of a surface, not something which is 3D or which has volume. It doesn't have any volume. It is just a cloth which, let's say, covers this triangle, and then you just take it on up till up there. And this is just a triangle, not even how the actual cloth would behave, but just to give you guys a visualization of how this would look like. So as we see here, what happens is, up until we have a value of 0.5 for U, and 0.5 for my V value as well, I see that this is always going to just be 0, right? So what I observe here is that if my U plus V is less than 1, then my copula takes a value of 0. And we observe this when only in terms of counter monotonic copulas, right? Where I say that my copula is the maximum of U plus V minus 1, 0, which is what you observe here. And now if you have a look at this graph, okay, this is maybe not that clear, I would say. But if you now you understand, right? So again, if you have 0 here and if you have 0 here for this guy, there is really no height. So 0 times 0 is going to be 0. But again, you see there is no height for this axis and that axis as well. So what it is telling you is how much ever value my U takes, if my V is 0, my copula is also going to be touched to the ground. So it is going to be 0 because any number times the 0 is going to give me a 0 again. And that is the same thing here. So see this as a cloth which only joins, which is only, touched to the ground on these two edges. And then you take it upwards and direct plug in, to something at this top right corner of your room. And that is how this independent copula would look like. So again, you have this edge, this edge, and that edge covered with a cloth. And maybe I guess for the minimum one. So of course, if this is counter monotonic, this is independence. This has to be monotonic one, which is the minimum of these guys. But I guess the shadow here is really not that great. Yeah. Okay, maybe let me just. Gone. Okay, forget about this. I don't know what's happening. I guess I lost the graph. But did you guys understand at least those two copulas? Oh yeah, this is what I'm talking about. Yeah, so if you guys have a look at this graph, yeah. So do you guys see the flatness here a bit? Give me a minute. Yeah, yes, I have it now. Yeah. So now can you guys see these three graphs clearly? Can you guys tell me which one is what copula now? Any one of you guys? DJ. Yes.
Pregnancy में कितना दिखावा 105 kg. Pregnancy with thyroid हमेशा.
What does this copula look like? I guess the audio is on for someone. Yes, anyone? So I guess this must be pretty easy because if you see this flat surface right here, we know that this is just counter monotonic, right? And because here you see something like this, you can imagine that this must be the independent copula. And here you see a straight line here, right? So this must correspond to the minimum one, which is just, the comonotonic copula. So remember the formula for the comonotonic copula was what? Minimum of u comma v. So let us say I give you guys a 1 here and I give you guys a 0 here for this, right? What is the value? What is the height? I mean, it still covers all of these edges, right? Because minimum of any number here with a 0 will always be 0 because we know that this u and v always take value between 0 and 1. We know that if one of these numbers is 0, then the minimum of these two numbers will also be 0. So you see this is again stuck to the ground, and yes, and then as in when you increase your value of u and v, it will take some height which will be measured here. And let us see what happens if we have 1 here and if we have 1 here. You will go there, and if you check its heights, if you check its height, it's again going to be 1 there because the minimum of 1 comma 1 is just going to be another 1. So I guess that was it about, these copulas. And again, now if you try to plot it using the utility diagrams that I just showed you guys. Yeah, so this is actually, how it looks like. So this is the upper bound, which is the counter monotonic, and this is how the comonotonic one would look like. And these are known as actually Frechet or Wolfgang upper lower bounds. I don't care about the pronunciation of this guy's name. But yeah, does this remind you of, oh, am I sharing? No, right? Yeah, so this is what I'm talking about. And this is how your counter monotonic copula would look like, and this is how your comonotonic copula would look like. And independence would be somewhere right in between these two. So if you know the bounds, if you want to know the bounds that your copula will have, the flaps, so that this flap and this flap, if you join them together, you get some of the floor covered and you get a closed pyramid kind of a shape, and that is what is the bound of your copula. So your copula should always lie within this bounds, and this is a special being upper and lower bound. So this would be your upper bound, right? This would be your upper bound and this would be your lower bound, I guess. So yeah, something like that. And do I have something else? No, I guess. So yeah, this would be about, the bounds of these graphs. And now let me go to our yeah. So yeah, so now if we were to draw these copulas in terms of the contour diagrams, what you would observe, I think the best is just to, share your book at this point. Is it okay if I continue the class for like, let's say, 5 or 6 minutes? I think I'm going to continue class. Let me just show you guys at least, how this look like. Yeah. So if you guys have a look now here, we see that we have independent copula, and it kind of looks like what I just showed to you guys, right? And again, so remember these are just similar to the indifference curves that we saw. And if you have a look at this thing here now, so this curve they say is 0.1, right? So what does this curve represent? This curve represents all the coordinates which when multiplied together will give you the answer 0.1. So if you have a look at 1 here, you see you will have to multiply it with 0.1 here, right? And you get a value of 0.1, and the same is the case here as well. So if you multiply this 1 with 0.1, you get 0.1, and such will be the case everywhere else as well. So let's say you would want to have 0.2 here and 0.5 there, right? And so will be the case for all of these values. And that is why this curves are how you represent the independent copula. But again, now let us have a look at the common atomic copula. So if I'm looking at a common atomic copula, what is my formula? It takes the minimum of u comma v, right? So let us say my u is this and my v is this. And if I tell you that my u is 0.2 and my v is 0.4, then what do you think will be the value of my copula? Minimum of 0.2 and 0.4, right? Which is going to be 0.2 itself. And let us now, let us say I give you guys a 0.6 for v. It will still be the same because the minimum of 0.2 and 0.6 will again still be just 0.2. So all of these values which give you a value of copula as 0.2 are represented by this curve here, okay? So it's talking about 0.2. So this particular curve represents the values of the coordinates that which when inserted here will give you a value for the copula as 0.2, and that is why you get these L-shaped graphs. So if someone is has studied economics, they would see this as some goods which are complementary to each other. But I guess what the very best example for that also would be, let's say, a right shoe and left shoe. You can't really function with just one shoe, right? You need to have those two shoes, right? One right and one left to be able to function. So let us say you have one left shoe and 3 right shoes. You can still only make one person wear a pair of shoe, right? The rest of these are waste. So you still get a utility of one, I would say. So that is where actually these L-shaped graphs come handy. And again, what happens is that is how you derive. So these are all the combinations that will give you a utility of 0.2. So of course you just join them together, and this is how you get at the end your copula to look like in a 2D space. So this is how it would look in a 3D space, and this is how it would look in a 2D space. The same thing. And the similar thing happens here with the common atomic one. So if you have a look, as we discussed, till this value is 0.5 until this value is 0.5, you get a 0 here, right? And as and when it increases the point-wise value, you get some value starting from 0.1, and again you would still have something in here, but it's actually not 0. So you would have 0 line somewhere here, and this would be 0.0001 or something like that. But again, let us see if you have 1 here and if you have 0 here. What do you get? You get nothing, right? Because 1 minus 1 is 0 and maximum of 0 and 0 is just 0. So you see nothing here. I mean, if you were, you would ideally be on this line, which is the line of 0. But again, let us say you have 1 here and you have 1 here. So what would you have? You get a utility level of 1. I mean, you will have your Copula value as 1, right? So I guess that is how this counter monotonic graphs would look like in case of a 2D representation of the same thing. Does this make sense? Any doubts so far? So I would say that's it for today. And we'll have our next lecture tomorrow itself. And I guess by tomorrow we'll also, be finished